And in the last talk of the session, Ningning is going to tell us about type inference techniques.
Hi. All right. Welcome everyone to the very last talk of this second to last session on the very last day of Popo. I promise you that this talk is going to be lightweight. I'm Ningning from the University of Toronto, and this is joint work with my student Andong. As you may have guessed from the title of this talk, this is basically a position paper. So we are not going to offer any new technical contributions in this talk, but instead we are going to start with our recent contributions to type inference techniques, but we'll take one step back and express the general picture we are pursuing and also draw people's attention to our recent work and hopefully also get more people to contribute to this direction. So we are at WITS', right, workshop on type system implementations. So I'm sure many of you are interested in or maybe already familiar with implementations of part of a type system. So if you read a paper on a type system, the paper typically starts with a Descartes system that provides a specification that specifies how the system should behave under different situations, and then maybe you would prove some properties about the system, like syntactical type soundness as an example. But the Descartes system does not correspond directly to implementation, right? So if you want to implement the type system, maybe there's also an algorithmic system that sort of tries to guide the implementation, and maybe sometimes writing explicit type annotations can be tedious. So you also want to perform some type inference, and you want to prove some properties about the algorithmic system as well. And this talk will focus on type inference, which is itself a very difficult problem, right? Because you have to know whether type inference is decidable, whether we can always infer the most general type, aka principal types. How do we handle subtyping? How do you handle unification? Do you need to perform a curse check? How do you manage the scope of variables? Can you prevent scope of variables from escaping, right? These are just the examples. And once you have this algorithmic system, right, there are usually proofs that says, the algorithmic system is sound and complete with respect to the Descartes system. So this is the general picture of a type system presentation that you can find on papers, especially papers on type inference techniques. In this talk, however, I argue that there is one additional component on the right of this picture, which is of equal importance to all the other systems, which is the actual implementation of the type inference algorithm. And the actual implementation is often the real beast, as it contains, lots of hacks, aka folklore, or low-level details necessary for the implementation to be performant. And in this talk, we will also often use GHC as an example, but a similar argument applies to many other type checkers as well. And once you have this implementation, right, ideally, you should also try to prove that this implementation is sound and complete with respect to the Descartes or the algorithmic system. This is important, right? Because you want to make sure that the implementation is actually doing what you think it is doing. However, formalisms of the actual implementation techniques, in my opinion, are often understudied in the literature. So there are many folklores or secrets that are maybe shared among many of us in the audience, but it's not very well specified, and sometimes they work, sometimes they don't. And until you prove that it's actually sound and complete, you do not know whether the algorithm is actually doing what you think it is doing. So the purpose of this talk is really to draw people's attention to these implementation techniques that to me are very important to make sure that the implementation is correct. And to convince you that this is really an important problem, I will give you two examples. And the first example is high-rank polymorphism. So if you have high-rank polymorphism, that basically means you have polymorphic types that appear contravariantly in a function type. Like in this case, we have this function f that takes a polymorphic function And this polymorphic function is for all A8 ways, not very interesting, but this allows us to apply this function to types of different arguments in the body. And if you look at the type of this whole expression, you can see that this polymorphic for all appears contravariantly in the function type, and this is actually a higher rank or rank 2 polymorphism. And with higher rank polymorphism, we need to be very careful with the scope of variables. So for example, if you look at the higher rank type system, there is usually a subtyping rule in the declarative system that says, if you want sigma 1 to be a subtype of for all A sigma 2, then you should check that first sigma 1 is a subtype of sigma 2, but also A does not appear in the free type variables of sigma 1. Because you want A to be fresh with respect to sigma 1, because sigma 1 is supposed to be more polymorphic than for all A sigma 2, whatever A is instantiated to later on, maybe. And if we consider the algorithmic system, right, there will be one corresponding rule that corresponds to that declarative rule. And in this algorithmic rule, so I assume we have some algorithmic context because you have unification variables. So this context, the gamma and the delta, they just map unification variables to their solutions. So if you want to check whether sigma 1 is a subtype of for all A sigma 2, you would first check whether sigma 1 is a subtype of sigma 2. But very importantly, we also need to translate that set condition in the declarative rule to set conditions in the algorithmic rule, right? And oftentimes, this is already not very straightforward, right? It's not very obvious. You look at the rule in the declarative system, and you say, OK, how should I translate that in the algorithmic rule? And in the algorithmic system, what happens is that you want to make sure the scolen variable A, in this case, does not escape in the solutions of unification variables that have wider scope than the scolens. So you would first apply this unification context delta to the type sigma 1, and you check that A does not appear in the free variable of that. And that one might be more obvious, but this one maybe is less, which is you should also check that A does not escape in the free variables, in the solutions of unification variables that appear in sigma 2. But this kind of check is actually quite subtle, right? First, you need to make sure that you are actually performing this kind of check. And this rule is also not that beautiful, right? And we like beautiful rules. And why is this not beautiful? Well, first, if you have nested polymorphism, right, of course, now you will have to perform this substitution many times. You have to traverse the type many times. You have to perform this check many times. And more importantly, right, your type system typically supports many other features as well. And they would come with many.
So I was expecting you to say that you check that alpha does not occur in sigma 1 nor in delta. And you have a different check. Surely this is right, but
because, well, it depends on how you implement it, because you can have unification variables that you would further create down the path that can actually refer to A.
Yeah, but would it be enough to say that A does not occur in delta at all?
No. This is what I'm saying. So if you have like another, for all, for example, right, and you would instantiate that for all with a unification variable, and you would say we can solve that unification variable with this A, and that is allowed. If that makes sense, like further unification variables created could refer to A. Yes.
Are you missing a binder on sigma 2 when you're checking the free type variables?
I'm missing a binder in sigma 2 when I'm checking.
If I do like full beta dot beta is a subtype of full alpha dot alpha, surely the right hand side of sigma 2 will contain alpha regardless of what I do in my typing context. That's correct. I think I may have done the set condition in the wrong way.
Which is probably proving your point.
Yes, that's true. But there is a second check that is needed. You can trust me on that. But as you can see, this is subtle. And you have many other similarly subtle set conditions in your type system likely, right? And this is actually not how people implement hierarchical polymorphism, for example, in GHC. And what actually happens in GHC is that people use levels, which is maybe a new term to many of you, maybe not. And levels themselves are not a new idea at all. And they are not even a new topic at WITS. because here is one slide I take from Samuel Peter Jones' talk at WITS 2024, and the slide mentioned that we should use level numbers for preventing existential escape. And here is another slide taken from Richard Eisenberg's talk just last year at WITS 2025. And the slide also mentioned we should use level numbers for left generalization, among other things. There are many other use cases of levels in that talk. And just to give some context about what this slide is saying, because we will get back to this later, this is about Hindley-Milner style left generalization, that we should use level numbers in order to perform more efficient left generalization. What does that mean? So if you look at the usual Hindley-Milner style generalization, you will see that we'll try to type check the binder of this expression, and we get this type top prime, and then we try to generalize it. And the process of generalization is we have to calculate the set of free variables, which is the difference between the free variables in this type tau minus all the free variables that occur in the context A. But as you can notice that if you do generalization this way, we have to traverse this whole context in order to calculate the set of free variables. And maybe your context can be really big, right? It contains lots of definitions, local variables, and you have to traverse it again for each generalization. So we should instead use level numbers. And level numbers themselves are a very old idea as well from 90s. This is the earliest reference I can find in a paper by in 1990s by Didier Remy. We omit details, but we will come back to that generalization very briefly later. But the important thing is, well, levels themselves are a very old idea, and they are widely used in language implementations of the type checkers for different purposes. So we are going to implement high-rank polymorphism, type inference for them as well, using levels that would allow us to manage the scope of variables in a more efficient and uniform way. So going back to this slide, right, what actually happened in the implementation, right, is not the rule we have on the left side of this slide. Instead, what's actually going to happen in the implementation is, well, first, typing is associated with a level number. The level number is bumped when entering the new scope of Scotland variables. And error unification Scotland variable is associated with the level at which it is created. And when performing unification, when we unify unification variable with the type, if the type contains the Scotland variable at a higher level, unification fails because the Scotland is escaping. And the type contains unification variables at a higher level, then you should lower their levels because you're basically narrowing the scope of these unification variables. And how can we make sure? So this is actually what happens in GACL, more or less, right? Of course, the actual implementation is more complicated because of other features. But how can we make sure that this implementation we have on this part of the slide actually corresponds to what happens, or what you claimed what the system is doing with the rule on the left of the slide. So this is the missing part, right? But before I answer this question, I also want to give you another example just to demonstrate our point more, right? And the second example is generalized algebraic data types, or GADTs, right? And the basic idea of GADTs, as you all know, is that we can capture very important invariants on the type level. Like in this case, we are declaring algebraic data type T that takes the type and returns the type. So it's star to star, and it has two data constructors, T1 and T2. And whenever you construct something using T1, we know that the type argument you provide to T is bool. So GADTs have been widely used as well for many applications, but it's also well known that GADTs will cause problems for type inference. For example, in this case, we are defining this function f that takes two arguments, x and r, and we will perform a pattern matching on x. If x is t1n, we are going to return whether n is greater than 0. If f is t2, then we'll just return r, which is the second argument to f. And if you think about what happens during type checking, right, in the first branch, we would have an invariant. So if you think the type of x is some TA, you would have this equivalence that A is equivalent to bool in the very first branch. And if you think about, what types you can actually assign to this program, there are actually two incomparable types. They are incomparable because no one subsumes the other. So the first type is for all A, TA to bool. This is a case where we think the type of the first branch is bool. And if the type of the first branch is bool, then R in the second branch needs to be bool. So the second argument to the function has type bool. Or because we have A is equivalent to bool, we could say the type of the first branch is A. In that case, R would have type A, and so the whole type is TA to A state. So this is a well-known challenging, right? It's like a type inference for GADTs. Has many difficulties, and there have been lots of work in that direction as well. And one particular approach we would focus on in this talk is this approach called outside in that is published at ICFP 29. And so the key idea of outside in, right, is that whenever you create a constraint, here I have two rules from the paper. So this is one rule, one typing rule for case expressions, and the case expressions use the typing rule for patterns. And when you create constraints in the typing rule for patterns, you create what people call implication constraint. And the implication constraint is basically saying that I have a set of untouchable variables, and the set of untouchable variables are variables that cannot be touched or unified within this constraint. And we have that there are some type equivalents, this D introduced by this GADT branch, and you should solve the rest of the constraint. And one important thing is, if you look at the set of untouchable variables, it includes all the free unification variables in the context, the gamma, as well as the type of the scrutiny and the return type of this branch, which are passed in when the case rule calls the typing rule, that alphas and beta created in that rule. And with the idea of outside in, what happens is we would reject programs without principal types, because those unification variables would be untouchable within the branch. So if we go back to this example, what would happen is that the return type of this function is actually untouchable within this branch. So you cannot solve the constraint that the return type of this whole branch is bool or A. This constraint will just remain unsolved until the end, so this program will just fail to type check. Again, we will not be talking about the details, as they are not that important in order to understand our point. So what's our point? Well, the point is, we need to calculate this set of untouchable variables. And you can see that we are again traversing this whole typing context, the gamma, in order to calculate the set of free unification variables. And this is very similar to the inefficient led generalization we had before, right? So we would imagine that, we would be able to use levels to solve a similar problem. So what actually happens in the implementation of GHC? Again, because we would like to apply levels, what happens is, well, typing is associated with a level number. The level number is bumped when entering the scope of pattern matching, especially pattern matching for GADT. And every implication constraint is associated with a level that indicates untouchability. And and we only solve touchable variables, right? There's this notion of untouchability that is introduced in this outside-in approach. But again, very importantly, right, we are missing an argument, right? These two rules on the left are quite complicated already, right? And are you sure that your implementation is actually doing what the algorithmic system says that it's doing, or maybe the declarative system? And what is worse? These two rules are not the whole picture, right? Because the original outside-in paper also includes the rule for let expressions. So we are also performing let generalization. So what happens in the let generalization is that we would first generate some constraints, F1, and we will try to solve all the simple constraints. There is some definition of simple constraints. You don't have to understand the details. And if after you solve all the simple constraints now, I will do this let generalization in this traditional Hindley-Milner style. But we already know that performing let generalization this way is not very efficient, right? So we should use levels. in order to perform left generalization. So now we are in a system where we use levels for multiple purposes, right? We use it for left generalization, we use it for GADTs in this case. And interestingly, the combination of this multiple purposes, multiple uses of a level actually cause very interesting consequences. So consider this program, right? This is the algebraic data type T we have, and we have this program bet. And in this program bet, we have a local letter expression. So we are trying to bind y to the expression not w, and then we just return false. This is just a minimal example to demonstrate the point. And in the second case, we just return false. So what happens in this example is because we have a letter expression, right? And left generalization says, solve this constraint now. I want to perform generalization. And this constraint, like return type of not w is bool, is indeed a simple constraint. But we are also inside a GADT branch. So the outside in says, w should be untouchable, or the type of it should be untouchable within this branch, because w is one of the argument of this function whose scope is not within this branch. So should I solve this constraint now or not, right? And if you think about it, this program is actually also does not have principal types. So we should reject it exactly because the return type of this, the type of w might be b, might be a or bool exactly because of the equivalence we have in the GADT branch. So this program should be rejected. But if you actually try it in GHC, you would find that this program, surprisingly, is actually accepted. So what happened? So we fired a bug report to GHC, right? There are some untouchable unification variables, that got wrongly solved. And after we submitted this bug report, Simon fixed it, right? In about 2 weeks. And in Simon's words, this is a very bad untouchability bug. And this bug has been in GHC in more than 10 years since outsiding is introduced. And to be clear, the formalism of outsiding in that paper is still correct. And the reason of this bug is exactly because the implementation is doing something different from what's described in the paper. And this difference causes some corner cases in the design of the system where you use levels for different purposes and got a surprising result for programs like this. So I hope I have convinced you successfully that we should pay more attention to the implementation of type inference techniques. And this is exactly what we have been doing. And as an example, we had a system with high rank polymorphism that is level-based. We use levels to perform type inference, and you can see that this whole typing judgment is now indexed with the level, and we use levels to manage the scope of columns and unification variables in the algorithmic system as well. And you can read more details in this paper we had last year at PLDI, and in that paper we supported both left generalization, high rank polymorphism, and local data types, and there are some case studies that discuss how GHC and OCaml use levels for different parts of a type checker. We also have an implementation in Coca and does some mini benches for the performance. And we are still working in this direction. So for ongoing and future work, we are currently working on a formalism, a level-based type inference algorithm for GADTs. And I'm also interested in having a full mechanism, full mechanization in ROC. We had some mechanization in the PLDI paper about the declarative system, but we do not have it for the algorithmic system. And we are also interested in techniques beyond levels. For example, techniques people use to support type families, as an example in GHC. And we are also interested in other languages such as OCaml. And more broadly, right, if there are other hacks that you would like to see formalized, please talk to us, and we'll be very happy to talk about it. That's all my talk.
Thank you. So in this slide, you mentioned that you want to go beyond GHC, for example. OCaml does similar expressive type inference as well, but because OCaml is a mutable language, so they have these references, and maybe they also have shared references to simplify the constraint. So do you think it's kind of feasible to really extend, or how faithful do you expect that we can push this limit towards a realistic implementation in this direction? So do you think there's a boundary, or do you think what techniques or what automation do we need to really like make it go further? Yeah, thank you.
Right, that's a very good question. So, well, GHC internally use multiple variables as well in their type checker. So there's no huge difference between the two languages. But they do use different techniques for different reasons because they have different set of features. But more broadly, I think our ultimate goal is, of course, to have a fully mechanized, well-studied type inference technique, for all these different languages. And one of these challenges, as I can imagine, is this multiple variables technique that people actually use, right? Because now you would like to reason about the functionality of the type inference at the pure level, but internally it's actually using all those multiple variables. I think there are definitely challenges there, but it also makes this problem really interesting, right?
Another question?
Yeah, the first audience says he compared with the OCaml style and the Haskell style. Do you really consider another languages like OOP style instead of those are the functional programming languages, right?
Very good question. I think I'm interested in that, but I'm not an OOP researcher. But I would be interested in talking to people in OOP languages about hacks used in Scala or maybe Java. What kind of hacks, aka folklores, that are used there.
Liner, the GHC behavior, I'm actually curious, was that sound? Because I do feel like, and also like, what did the error message look like after you fix it? Because I feel like a lot of users might actually be confused as to why that didn't type check.
Well, it would say that some unification variable is not touchable, which is a little bit mysterious, arguably.
Like was the original behavior sound? You'd say, obviously, you haven't proved anything about it, but I'm curious.
What's your definition of soundness to some degree? Because your system says this program should be rejected, but you accepted it.
Oh yeah, no, it's obviously unsound with respect to the formalization. But I'm thinking in terms of more like our goal here is to try to figure out what type this program has, and this program has a type.
Right.
Like the question is essentially, does the system ever actually assign a type to a program that it doesn't really have? And in which case, is there actually an advantage to using the formalized system versus trying to formalize this system? Or in general, I guess since you asked me the philosophical question, like, doesn't it make more sense to first just give the basic type system, like say system F, and then almost have the typing of non-annotated things be almost an implementation detail. You want it to be sound, but that's all you care about.
Right. So I think it depends on whether you want principal types for your type inference technique. If there are more than one type that is, that you can assign, and there are multiple ones that are incomparable, then arguably one should reject it because, if you choose one and you precede it, maybe certain later in the program, this program gets rejected again because of other reasons. But if your implementation, mysterious, they pick the other approach, maybe other type, then maybe it will get accepted, right? Now you cannot predict what happens with your program because it depends on what you do in assigning the types when there are no principal types.
Thank you very much.
Thank you.